Close your eyes for a moment. Picture the night sky, not as a flat canvas, but as an ocean of impossible depth. See the distant galaxies not as tiny specks of light, but as entire islands of existence, each containing billions of stars, billions of worlds. For most of human history, we believed this cosmic ocean was slowing down, its expansion gradually succumbing to the pull of gravity, like a wave falling back upon itself. But we were wrong. Something invisible, something unknown, has its hand on the throttle. The universe is not slowing down, it's accelerating. A phantom force is pushing everything apart, faster and faster, into a future we cannot yet comprehend. What is this force? We call it dark energy, but giving it a name doesn't solve the mystery. In this journey, we will explore one of the most profound and unsettling possibilities ever conceived, that this ghost in our cosmos is not from our universe at all. Prepare to question the very dimensions of your reality as we seek a phantom from another world. Our story begins not in the far future, but in the early 20th century, with a man who reshaped our understanding of gravity itself. Albert Einstein, with his theory of general relativity, showed us that space and time are not a static stage, but a dynamic fabric, warped and woven by mass and energy. When he applied his equations to the entire universe, they told him something strange. The universe should either be expanding or contracting. It could not stand still. But in Einstein's time, the prevailing view was of a static, eternal cosmos. To make his equations fit this belief, he added a term, a kind of cosmic anti-gravity, which he called the cosmological constant. It was a mathematical fudge factor, a placeholder to keep the universe in a delicate, static balance. But then in 1929, Edwin Hubble, peering through the Hooker telescope on Mount Wilson, made a landmark discovery. He observed that distant galaxies were all moving away from us, and the farther away they were, the faster they were receding. The universe was not static, it was expanding. Einstein reportedly called his cosmological constant his biggest blunder. The fudge factor was unnecessary. For decades the story seemed settled. The universe was expanding from the Big Bang, and the gravity of all the matter within it was acting as a brake, gradually slowing it down. The only question was whether there was enough gravity to stop it completely and cause a big crunch, or if it would expand forever, slowing into a cold, dark eternity. But in 1998, the universe threw us the biggest curveball in the history of science. The blunder, it turned out, was not the answer, but it was pointing at the right question. So, how did we discover that the brakes were broken? The key was to find a standard candle in the cosmos, a type of object with a known consistent brightness which we could use to measure vast cosmic distances. Imagine you're in a completely dark field and you see a single candle flame. You can't know if it's a faint candle right in front of you or a very bright candle far away. But if you know that all candles of a certain type have exactly the same intrinsic brightness, you could tell its distance just by how dim it appears. In cosmology, our standard candles are a special type of exploding star known as a Type 1a supernova. These cataclysmic events occur when a white dwarf star, the dense remnant of a star like our Sun, pulls too much matter from a companion star. When it reaches a precise, critical mass, it ignites in a runaway thermonuclear explosion. Because they all explode at the same mass, they all reach nearly the same peak brightness, a brilliance that can outshine their entire host galaxy. This makes them perfect for measuring the universe. Two independent teams of astronomers, the Supernova Cosmology Project and the High Z Supernova Search Team, spent years scanning the heavens, searching for these distant, fleeting explosions. They would compare the apparent dimness of these supernovae, and thus their distance with their redshift, which tells us how much the universe has expanded since the light left the star. Everyone expected to find that the expansion was slowing down. The data, they assumed, would show that the most distant supernova were brighter than they should be, indicating that the universe's expansion was faster in the past. But that is not what they found. The distant supernova were dimmer. They were farther away than predicted. The only way this could be possible is if the expansion of the universe had not been slowing down, but had been speeding up over the last several billion years. It was a discovery that shook the foundations of physics, earning the team leaders the Nobel Prize in 2011. The universe had its foot on the gas pedal, and we had absolutely no idea where the engine was. This unseen acceleration is the primary evidence, the smoking gun, for the existence of what we now call dark energy. The discovery of accelerating expansion created a profound problem. According to everything we knew about gravity, this shouldn't be happening. Gravity, as described by Einstein, is always attractive. The cumulative gravitational pull of all the galaxies, stars, gas, and dark matter in the universe should be acting like a cosmic brake, slowing the expansion that began with the Big Bang. Instead, we found an anti-gravity, a repulsive force, that is not just counteracting gravity but overwhelming it on the largest scales. This is where the term dark energy comes from. It is not dark in the sense that it's black. It's dark because we have no idea what it is. It is a placeholder for our ignorance. It doesn't interact with light. It doesn't seem to clump together like matter does. It appears to be smoothly distributed throughout the entire universe, a uniform pressure embedded in the fabric of space-time itself. To make matters even more bizarre, its influence is growing. In the early universe, when everything was much closer together, the attractive force of gravity dominated. The expansion was, in fact, slowing down. But as the universe expanded, the density of matter and dark matter decreased. The stuff of the cosmos got spread out. The density of dark energy, however, seems to be constant. It doesn't dilute as space expands. This means that as time went on, its repulsive effect became more and more significant, until, about 5 to 6 billion years ago, it reached a tipping point. Dark energy's outward push became stronger than gravity's inward pull, and the universe's expansion began to accelerate. We now live in an era of dark energy domination. Based on our best measurements, this mysterious substance accounts for roughly 68% of the total energy density of the universe. Normal matter, the stuff that makes up you, me, the planets, and the stars, is less than 5%. The rest, about 27%, is dark matter, another cosmic mystery. This means that everything we can see and understand is just a tiny sliver of reality. The vast majority of the cosmos is made of two components, dark matter and dark energy, that remain completely unknown to us. So, what could this dark energy be? The simplest and most widely accepted explanation takes us back to Einstein's biggest blunder, the cosmological constant. Perhaps it wasn't a blunder after all. In modern physics, the cosmological constant is reinterpreted as the energy of empty space itself, the vacuum energy. According to quantum field theory, a vacuum is not truly empty. It is a roiling, bubbling sea of virtual particles that constantly pop into and out of existence. These fleeting particles should, in theory, possess energy. This vacuum energy would be an intrinsic property of space-time, meaning it would have the same density everywhere and at all times. It wouldn't dilute as the universe expands. This perfectly matches the observed properties of dark energy. It would create a constant, negative pressure that pushes space-time apart, driving the cosmic acceleration we see. It's an elegant solution. It fits the data beautifully, and it arises naturally from our two most successful theories, general relativity and quantum mechanics, but there is a catch. And it is not a small one. It is, in fact, the biggest discrepancy between theory and observation in the history of science. When physicists try to calculate the theoretical value of this vacuum energy based on quantum mechanics, the number they get is catastrophically, comically wrong. The predicted value is about 10 to the power of 120 times larger than the value we actually observe from the cosmic acceleration. That is a 1 followed by 120 zeros. If the vacuum energy were truly that powerful, the universe would have been ripped apart in the first fraction of a second after the Big Bang. Stars and galaxies would have never had a chance to form. The fact that we exist to observe a much smaller, finely tuned value for dark energy is a profound mystery known as the cosmological constant problem. It suggests that either our understanding of quantum gravity is deeply flawed, or that some unknown physical principle is at play, cancelling out almost all of the vacuum energy, leaving just a tiny residual amount to drive the cosmic acceleration. The cosmological constant problem is so severe that it has led many physicists to seek alternative explanations for dark energy. Perhaps it isn't a constant energy of the vacuum, perhaps it's something else entirely, something dynamic and evolving. This class of theories is known as quintessence. The name comes from the ancient Greek concept of a fifth element, after earth, water, air, and fire. In this modern context, quintessence refers to a new, dynamic energy field that permeates all of space, similar to an electric or magnetic field. Unlike the cosmological constant, the energy density of this quintessence field can change over time and space. This is a crucial difference. If dark energy is a quintessence field, it wouldn't have been a constant presence throughout cosmic history. In the early universe, its energy density could have been much higher, playing a role in cosmic inflation, and then it could have decayed over time to the small value we observe today. This could potentially offer a more natural explanation for why dark energy is so weak now, avoiding the fine-tuning problem of the cosmological constant. The behavior of this field is described by its equation of state, a parameter denoted by the letter W. For a cosmological constant, W is exactly -1. For normal matter, W is 0. For radiation, W is 1/3. Quintessence models allow W to be a value other than -1, and it could even change over time. If W is between -1 and -1/3, the field still drives acceleration, but in a less extreme way than the cosmological constant. Cosmologists are working tirelessly to measure the value of W with extreme precision, using telescopes like the Euclid Space Telescope and the Vera C. Rubin Observatory. By observing how the cosmic acceleration has changed throughout history, they hope to determine if W is truly constant at -1 or if it has evolved. If they find even a slight deviation from -1, it would be a revolutionary discovery, ruling out the simple vacuum energy explanation and pointing towards a new, dynamic force of nature. But quintessence also introduces its own set of challenges, like why the field has the specific properties it does, and why its energy density today is so comparable to the density of matter. The mystery deepens. As if a dynamic field wasn't strange enough, there is an even more exotic and troubling possibility for the nature of dark energy. What if its equation of state parameter W is not greater than -1, but less than -1? This is the realm of phantom energy. At first glance, this might seem like a small mathematical tweak, but its physical implications are staggering and apocalyptic. While a cosmological constant provides a steady, constant push, and quintessence provides a dynamic but potentially gentle push, phantom energy is a force of ever-increasing intensity. If dark energy is phantom energy, its density does not remain constant as the universe expands. It increases. This creates a runaway feedback loop. As space expands, the density of phantom energy grows, which in turn causes space to expand even faster. This faster expansion leads to an even greater increase in phantom energy density, and so on. The acceleration itself accelerates. This scenario leads to a terrifying, ultimate fate for the universe known as the Big Rip. In the final moments of a Big Rip universe, the repulsive force of phantom energy would become so strong that it would overcome all other forces of nature. A few 100 million years before the end, it would be powerful enough to unbind the Milky Way galaxy, sending its stars flying into the void. A few months before the end, it would overcome the gravity holding solar systems together. The Earth would be torn away from the Sun. In the final minutes, planets and stars would be ripped apart. In the last fractions of a second, atoms themselves would be disintegrated as the phantom force overwhelms the strong nuclear force. Finally, space-time itself would be torn asunder, and the universe would end in a singularity of infinite density and scale factor. While current observational data is consistent with W being -1, it does not yet rule out the possibility that W is slightly less than -1. The phantom energy scenario remains a terrifying, albeit unlikely, possibility on the table. It represents a fundamental challenge to our understanding of physics, as it violates certain energy conditions that are typically assumed to hold true. But the universe has surprised us before, and the Big Rip serves as a stark reminder of how little we truly know about the ultimate cosmic endgame. The profound challenges presented by the cosmological constant, quintessence, and phantom energy have pushed some theorists to consider a truly radical idea. What if dark energy isn't a new substance or field within our universe at all? What if we've been looking in the wrong place? This line of thinking asks us to reconsider our most basic assumptions about reality, specifically our assumption that we live in a universe of 3 spatial dimensions and 1 time dimension. This is the gateway to one of the most mind-bending concepts in modern physics, string theory, and its implication of extra dimensions. String theory is an attempt to be a theory of everything, a single theoretical framework that unites Einstein's general relativity, the theory of the very large, with quantum mechanics, the theory of the very small. In its quest for unification, it makes an extraordinary prediction. The universe does not have just the 3 spatial dimensions we experience. It must have additional, hidden spatial dimensions. In the most popular versions of the theory, there are a total of 10 spatial dimensions. So where are they? Why don't we see them? The theory suggests that these extra dimensions are compactified, curled up on themselves at an incredibly tiny scale, far smaller than an atom, at the so-called Planck length. Imagine a garden hose. From a great distance, it looks like a one-dimensional line, but if you get very close, you see it has a second dimension, the circular circumference you can travel around. The extra dimensions of string theory are thought to be like that circumference, curled up so small that we can't perceive them in our everyday lives. This isn't just a mathematical curiosity. The geometry of these hidden dimensions is not arbitrary. The precise way in which they are curled up and shaped, the Calabi-Yau manifold, determines the fundamental constants of nature, the masses of particles, and the strengths of the forces in our 3-dimensional world. It suggests that our universe's properties are a direct consequence of a higher dimensional geometry. And this is where things get really interesting. What if not all forces are confined to our 3 dimensions? What if gravity, the force that shapes the cosmos, is different? The idea of extra dimensions leads to a specific set of models known as Brane cosmology, which provides a radical new stage for our cosmic drama. The name comes from the word membrane. In these theories, our entire three-dimensional universe is a brane, a vast membrane-like surface existing within a much larger, higher dimensional space known as the bulk or hyperspace. Imagine our universe as a single sheet of paper floating in a room. We and all the particles and forces that make up our reality, like electromagnetism and the nuclear forces, are stuck to the surface of this paper. We can move forward and backward, left and right, and up and down along the paper, but we cannot leave its surface. The particles and forces are described in string theory as open strings with their ends tied down to our brane. We are, in a sense, flatlanders, living out our existence completely unaware of the larger, higher dimensional room that the paper is floating in. However, Brane cosmology proposes that there is one fundamental force that is not confined to our brain: gravity. In string theory, the particle that carries the gravitational force, the graviton, is described as a closed loop of string. Because it has no ends to tie it down, it is free to travel off our brain and explore the full, higher dimensional bulk. This has a profound consequence. It could explain why gravity is so much weaker than the other fundamental forces. The reason gravity feels so feeble, you can overcome the entire gravitational pull of the Earth with a simple refrigerator magnet, is because its strength is leaking out into the extra dimensions. Most of the gravitons are not interacting with our brain. They are floating around in the bulk. We only feel a tiny fraction of gravity's true strength. This elegant solution to the hierarchy problem is one of the main motivations for Brane cosmology. But it also opens a door to even more spectacular possibilities. If gravity can travel through the bulk, what else might be out there? Could there be other branes, other parallel universes floating just a microscopic distance away from us in a hidden dimension? And could the physics of the bulk be influencing the evolution of our own universe? If our universe is a brane floating in a higher dimensional bulk, then the cosmological constant problem might not be a problem with our universe at all, but a problem of our limited perspective. Perhaps the enormous vacuum energy predicted by quantum field theory is real, but its gravitational effects are being cancelled or modified by the physics of the bulk and the extra dimensions. In some brane world scenarios, the geometry of the extra dimensions can naturally alter how energy on the brane affects space-time. For example, in the Randall-Sundrum model, two branes are placed in a warped, five-dimensional space-time. The warping is so extreme that it dramatically dampens the effect of gravity, providing a potential solution to the hierarchy problem. This warping could also affect the cosmological constant. The huge vacuum energy on our brane might be precisely counterbalanced by the tension of the brane itself or by properties of the bulk space-time, leaving only the small residual value we observe as dark energy. It's as if the bulk is acting as a cosmic regulator, protecting our universe from the explosive energy of its own vacuum. More excitingly, this framework opens the door for dark energy to be a truly higher dimensional phenomenon. What if the acceleration of our universe is being caused by something happening not on our brane, but in the bulk? It could be the gravitational influence of another parallel brane floating nearby in the bulk. The gravitational pull between our brane and this shadow brane could manifest in our 3D universe as an apparent acceleration, a phantom force whose origin is completely hidden from us, or it could be energy fields that exist only in the bulk. These bulk fields could interact gravitationally with our brane, their energy density pushing our universe apart. In this picture, dark energy is literally leaking into our universe from another dimension. It would be a ghost in the cosmic machine, a force whose source is fundamentally inaccessible to us, forever beyond our direct observation, knowable only through its gravitational shadow cast upon our world. This is no longer just a matter of adding a new particle or field. It is a complete reimagining of the very stage on which the cosmos performs. Our universe ceases to be everything and becomes just one part of a much larger and much stranger meta-reality. Let's delve deeper into this phantom force from another dimension. How exactly could a higher dimensional bulk generate the effect of dark energy on our brain? One compelling idea is known as the self-accelerating brain world model, or the DGP model, named after its creators Diwali, Gabadadze, and Parati. In this scenario, there is only one brain, our universe, but it exists in an infinite volume extra dimension. The key idea is that gravity behaves differently on different distance scales. On smaller scales, like within our solar system or even our galaxy, gravity is effectively trapped on our brain, and it follows the familiar inverse square law of Newton and Einstein. This is why general relativity works so well for predicting the orbits of planets and the bending of starlight. However, on vast cosmological scales, gravity is no longer confined. It begins to leak out into the infinite bulk dimension. This leakage of gravity over enormous distances has a strange and counterintuitive effect. It weakens the gravitational pull between distant galaxies, making it appear as if a repulsive force is pushing them apart. In this model, dark energy isn't a substance at all. There is no new energy field, no vacuum energy. The acceleration is an illusion, a modification of gravity itself that only becomes apparent when you look at the universe on the largest possible scales. It's a feature of the higher dimensional geometry. This is a tantalizing prospect because it solves the mystery of dark energy without inventing any new stuff. The acceleration is simply a consequence of the universe having more dimensions than we can see. The model makes specific, testable predictions. For example, it predicts that the growth of large-scale structures like galaxy clusters should be different than in a universe with standard dark energy. By studying how these structures form and evolve over cosmic time, we can test whether gravity is indeed behaving differently on large scales. While initial tests have put some pressure on the simplest version of the DGP model, the general concept of modified gravity from extra dimensions remains an active and exciting area of research. It forces us to ask a fundamental question. Are we seeing the effects of a mysterious energy, or are we misinterpreting the laws of gravity itself? The concept of branes and a bulk opens up a veritable Pandora's box of cosmological possibilities. If there can be one extra dimension, why not more? And if there can be other branes, what forms might they take? Some theories propose scenarios far more complex and dynamic than a simple parallel universe. One such idea is the ekpyrotic or cyclic universe model. In this vision, the Big Bang was not the beginning of time. Instead, it was the result of a collision between our brane and another brane in the higher dimensional bulk. Imagine two parallel universes, or branes, floating through hyperspace. Over immense eons, they are drawn towards each other by the gravitational forces in the bulk. Eventually, they collide. This cataclysmic collision releases a tremendous amount of energy on the branes, heating them to incredible temperatures and densities. This energetic event is what we perceive as the Big Bang. From there, the branes bounce apart and our universe begins its long period of expansion and cooling. The matter, radiation, and structure we see today are all imprints of the conditions during that cosmic smash-up. But the story doesn't end there. As the universes expand, dark energy, which in this model can be related to the potential energy between the branes, begins to dominate, causing the expansion to accelerate. This eventually smooths out the branes, preparing them for the next cycle. Over trillions of years, the branes will once again begin to approach each other, leading to another collision, another Big Bang, and the rebirth of the cosmos. In this model, time is infinite. The universe has no beginning and no end, only an endless cycle of collision, expansion, and contraction. Dark energy is not a mysterious substance, but the very force that drives the cycle, the engine of cosmic renewal. This is a profound philosophical shift. It replaces a single, one-off creation event with a timeless, cyclical process. While observationally distinguishing this from a standard Big Bang model is incredibly difficult, it presents a compelling narrative where dark energy plays a central creative role in the life of the multiverse. How could we ever hope to test these incredible dimension-spanning theories? It might seem like pure speculation, forever beyond the reach of experiment. But physicists are ingenious. They are devising ways to search for subtle clues, for tiny cracks in our 3D reality that might hint at a larger world beyond. One of the most direct ways to search for extra dimensions is at particle accelerators like the Large Hadron Collider, LHC, at CERN. The logic is as follows. When we smash particles together at incredibly high energies, we are probing the structure of spacetime on the smallest possible scales. If there are extra dimensions, it's possible that a high-energy collision could create a graviton that is kicked off our brane and escapes into the bulk. From our perspective on the brane, this would look like energy and momentum have suddenly vanished from the experiment. The detectors would record the debris from the collision, and the numbers just wouldn't add up. This missing energy signature would be a telltale sign of gravity leaking into the bulk. So far, the LHC has found no definitive evidence of this happening, which places strong constraints on how large these extra dimensions can be, if they exist. Another potential avenue is through gravitational waves. These ripples in space-time, first detected by LIGO in 2015, travel across the cosmos at the speed of light. According to some brane world theories, gravitons can take a shortcut through the bulk. This could mean that gravitational waves from a distant event, like the merger of two neutron stars, might arrive at our detectors a fraction of a second before the light from that same event. The detection of such a time gap would be revolutionary, providing direct evidence that gravity experiences a different geometry than light. Furthermore, some theories predict that the presence of extra dimensions could lead to the creation of microscopic black holes at energies accessible to the LHC. These would not be the planet-eating monsters of science fiction, but tiny, fleeting objects that would evaporate almost instantly through Hawking radiation, leaving a unique spray of particles in the detectors. Finding such an event would not only confirm the existence of extra dimensions, but also open a window into the bizarre world of quantum gravity. Beyond the high-energy realm of particle colliders, cosmologists are searching for the fingerprints of extra dimensions on the largest of scales. In the faint afterglow of the Big Bang itself, the cosmic microwave background, CMB. The CMB is a snapshot of the universe when it was just 380,000 years old. The tiny temperature fluctuations in this ancient light are the seeds from which all cosmic structures, including galaxies and clusters of galaxies, eventually grew. The precise pattern of these hot and cold spots on the CMB map contains a wealth of information about the fundamental parameters of our universe. If extra dimensions exist, they could have left subtle imprints on this pattern. For example, fluctuations in the brane itself, tiny brane wiggles, could have been stretched to cosmological sizes during the inflationary period of the early universe. These would show up as specific, non-random patterns in the CMB temperature map. Scientists are meticulously analyzing the data from missions like the Planck satellite, searching for these telltale signatures. Another potential clue comes from the cosmic gravitational wave background. Just as the early universe was filled with a hot plasma of particles, it should also have been filled with a sea of primordial gravitational waves generated during inflation. These waves would stretch and squeeze space-time, leaving a characteristic twisting pattern known as B-mode polarization in the CMB light. Brane cosmology models, particularly the cyclic and ekpyrotic scenarios, predict a very different gravitational wave background than standard inflation. Specifically, they tend to produce far fewer gravitational waves. If we search for these primordial B-modes and find that they are absent or extremely faint, it could be a powerful piece of evidence in favor of these Brane collision models. The search for these elusive signals is one of the primary goals of next-generation CMB experiments, like the Simons Observatory and CMBS-4. By studying the universe's first light with unprecedented precision, we might just find a shadow of a higher dimension imprinted on the cosmos from the moment of its birth. Let's pause and address a common misconception. When we talk about parallel universes in the context of Brane cosmology, it's crucial to distinguish it from the many-worlds interpretation of quantum mechanics. The many-worlds interpretation is a different concept entirely. It posits that every time a quantum measurement is made, the universe splits into multiple branches. In one branch, the particle is spin up, in another, it's spin down. This creates an ever-branching tree of parallel universes, each one a slightly different version of our own history. These quantum worlds are not physically separated from us in another dimension. They are all superimposed in the same space, but they cannot interact or communicate with each other. Brane cosmology, on the other hand, proposes a physical, spatial separation. The other branes, or parallel universes, are not just different outcomes of our history. They could be governed by entirely different laws of physics. The geometry of their own curled-up dimensions could be different, leading to different particle masses and force strengths. They are physically distinct places in the higher dimensional bulk. This leads to a fascinating and humbling idea, the anthropic principle. If there are countless branes out there in the bulk, each with different physical laws, then it's no surprise that we find ourselves living in a universe with a cosmological constant that is small enough to allow for the formation of galaxies, stars, and life. If it were any larger, we simply wouldn't be here to observe it. In most other Brane universes, the cosmological constant might be huge, tearing them apart instantly, or it might be strongly negative, causing them to collapse in a big crunch before life could ever arise. Our universe, with its finely tuned value for dark energy, is not special because it was designed that way, but because it is one of the few hospitable islands in a vast, mostly sterile, multiverse archipelago. We won the cosmic lottery. This multiverse explanation for the cosmological constant problem is compelling to some, as it avoids the need for a new physical principle to explain the fine-tuning. However, it's frustrating to others, as it seems to relegate a fundamental question to a matter of chance, potentially placing it beyond the reach of testable science. The idea that dark energy is a force from another dimension has profound implications for the ultimate fate of our universe. As we've discussed, if dark energy is a form of phantom energy, the universe could end in a big rip. In the context of Brane world models, a big rip could be triggered by exotic physics in the bulk. For instance, our brane could be falling into a region of the bulk with a different, more violent form of energy, or it could be colliding with a singular brane that tears our space-time apart. However, Brane cosmology also offers other, less violent but equally strange fates. If dark energy is related to the interaction between our brane and another, that interaction could change over time. Imagine another brane slowly drifting away from ours in the bulk. This could cause the repulsive force we feel to weaken over billions of years. The cosmic acceleration could slow, stop, and even reverse, leading to a period of contraction and a potential big crunch, setting the stage for another cycle. Another possibility is a phase transition. The vacuum energy of our universe, the very thing that might be driving the expansion, might not be in its most stable state. It could be in a false vacuum. Like a ball resting in a small dip on the side of a large hill, it is stable for now, but it's not at the lowest possible energy state. A quantum fluctuation, perhaps triggered by an interaction from the bulk, could nudge the ball over the edge. This would cause our universe's vacuum to decay into a new, true vacuum state. Such an event would propagate outwards at the speed of light, a bubble of true vacuum expanding and erasing our current reality. Inside the bubble, the laws of physics could be completely different. It would be the ultimate end, a complete rewriting of the rules of existence. Brane world scenarios could make such a transition more likely, as interactions with other branes or bulk fields could provide the nudge needed to push our false vacuum over the edge. The ultimate destiny of our cosmos may not be written in the stars of our universe, but in the unseen geometry and dynamics of a higher dimensional reality. If gravity can leak between dimensions, it begs the question, can anything else? The standard Brane world models assume that all the particles and forces of the standard model are confined to our brane. But is this necessarily true? Some more speculative theories explore the possibility that other particles could also travel through the bulk, albeit with much more difficulty than gravitons. This could provide an intriguing connection between two of the biggest mysteries in cosmology, dark energy and dark matter. We know that dark matter, which makes up about 27% of the universe, interacts with our world primarily through gravity. It doesn't seem to interact with light or normal matter in any other significant way. What if dark matter is simply normal matter that resides on a parallel brane, very close to our own? We wouldn't be able to see or touch it, but we would feel its gravitational pull across the small dimensional gap. In this scenario, the dark sector is not a collection of new, exotic particles, but a shadow world, a complete parallel set of particles and forces existing on a nearby brane. The interaction between our brane and this dark brane could be the source of both dark matter, the gravitational pull of the brane itself, and dark energy, the repulsive force or potential energy between the two branes. This brainwashing idea elegantly ties the two great cosmic unknowns together into a single, coherent picture rooted in higher dimensional physics. Furthermore, if particles can hop between branes, even if it's a very rare event, it could lead to observable phenomena. For example, some theories suggest that neutrons could occasionally oscillate into a sterile, mirror neutron on a parallel brane for a short time before returning. Experiments are being designed to search for this effect by seeing if neutrons appear to vanish and then reappear as they pass through strong magnetic fields. Finding such an oscillation would be earth-shattering evidence for a parallel world existing just a fraction of a millimeter away from us in another dimension. The phantom force of dark energy might not be a lone ghost, it might be part of an entire hidden ecosystem, a dark reflection of our own reality, separated by a dimensional veil. The concept of extra dimensions, while seemingly born from the abstract mathematics of string theory, actually has historical roots. The idea was first seriously proposed in the 1920s, not to explain dark energy, but in an attempt to unify gravity and electromagnetism. The mathematicians Theodore Kaluza and Oscar Klein theorized that if the universe had a fourth spatial dimension curled up into a tiny circle, then the equations of general relativity in 5 dimensions would naturally split into 2 sets of equations in 4 dimensions. One set would be Einstein's equations for gravity, and the other would be Maxwell's equations for electromagnetism. It was a beautiful and elegant idea. The electromagnetic force was simply a manifestation of gravity in a hidden 5th dimension. The theory ultimately failed to fully describe the real world, as it couldn't incorporate the other forces or particles that were later discovered. However, the core idea that the physics we see is a lower dimensional shadow of a richer, higher dimensional reality never went away. It lay dormant for decades until it was resurrected and expanded upon by string theory in the latter half of the 20th century. What is so compelling about this approach is that it offers the possibility of explaining why our universe has the properties it does. Instead of just measuring fundamental constants like the strength of gravity or the charge of an electron, these theories suggest that such values are not fundamental at all. They are consequences of the geometry of the extra dimensions. If we could somehow map the shape of those hidden dimensions, we could, in principle, derive these constants from first principles. Dark energy in this context is not just a random number to be measured. Its value would be deeply connected to the overall topology and geometry of the higher dimensional space. Solving the mystery of dark energy, therefore, becomes linked to solving the mystery of space itself. It's a holistic view of the cosmos where everything is interconnected. The push that is accelerating galaxies apart is tied to the same fundamental reality that governs the pull of a magnet on your refrigerator. It suggests a universe that is not a collection of disparate parts, but a single, unified geometric object, most of which remains hidden from our view. Let's bring this back to the cosmic scale and look at the evidence again. One of the powerful tools we have for probing the nature of dark energy is the study of how large-scale structures form in the universe. The cosmic web, the vast network of galaxy clusters, filaments and voids, grew from the tiny density fluctuations seen in the cosmic microwave background. The way this web has grown over billions of years is a battle between two competing forces, the inward pull of gravity from both normal and dark matter, which tries to clump things together, and the outward push of dark energy, which tries to pull everything apart. By measuring the distribution of galaxies at different points in cosmic history, we can map the history of this cosmic tug-of-war. If dark energy is a cosmological constant, its effect on structure growth will be different than if it's a dynamic quintessence field. And if the acceleration is caused by a modification of gravity due to extra dimensions, like in the DGP model, this too will leave a unique signature on the growth of structures. These modified gravity theories often predict that structure growth will be suppressed or altered in a specific, scale-dependent way. Projects like the Dark Energy Survey, DES, and the upcoming Legacy Survey of Space and Time, LSST, at the Vera C. Rubin Observatory are designed to do exactly this. They are mapping the positions and shapes of hundreds of millions or even billions of galaxies over a huge swath of the sky. By analyzing subtle distortions in the shapes of these distant galaxies, a phenomenon known as weak gravitational lensing, they can reconstruct the distribution of dark matter and trace the growth of the cosmic web over time. This data allows us to directly measure both the expansion history of the universe and the growth history of structure. Comparing these two measurements is a powerful test. Standard dark energy models based on general relativity make a firm prediction about how these two histories should relate. If we find a discrepancy, if the universe's structure grew in a way that doesn't match its expansion history, it would be a smoking gun for a modification of gravity, potentially pointing towards the influence of hidden dimensions. Another fascinating implication of the extra-dimensional theories for dark energy relates to black holes. These gravitational behemoths are the most extreme objects in the universe, representing a point where our current understanding of physics breaks down. In a standard 4D universe, black holes are relatively simple objects, described by just their mass, charge, and spin. But in a universe with extra dimensions, they could be much more complex. Theories like Brane cosmology predict the existence of black strings or black branes, higher dimensional black holes that extend into the bulk. From our 3D perspective, we would only see a small slice of such an object, which would appear to us as a regular black hole. However, these higher dimensional black holes would have unique properties. For instance, they might evaporate via Hawking radiation differently than their 4D counterparts, potentially radiating gravitons into the bulk dimensions. The gravitational waves emitted when two such objects merge would also carry signatures of the extra dimensions. The precise ring-down of the final black hole, the way it settles into a stable state after the merger, would have a different frequency spectrum if the black hole has access to more dimensions to radiate into. The LIGO-Virgo-Cagra collaboration is already using gravitational wave signals from merging black holes to test the predictions of general relativity in the strong field regime. As the sensitivity of these detectors improves, they may be able to look for these subtle deviations that could hint at extra-dimensional physics. Furthermore, some speculative models propose that the dark energy we observe could be related to the process of black hole formation itself. One idea suggests that black holes are not just absorbing matter, but are growing in a way that couples to the cosmic expansion, their increasing mass contributing to the dark energy density. While highly speculative, this connects the largest mystery of cosmology, dark energy, to the largest mystery of gravity, the black hole singularity. It suggests that the answers we seek about the cosmos may lie hidden inside its darkest, most enigmatic objects. The introduction of extra dimensions doesn't just offer new explanations, it also forces us to reevaluate what we thought we knew. Take, for example, the fundamental constants of nature. We assume they are just that, constant. The speed of light, the gravitational constant g, the fine structure constant that governs electromagnetism, we believe these are unchanging values woven into the fabric of reality. But if our universe is a brane, and its properties are determined by the geometry of the bulk, who is to say that this geometry is static? If the size or shape of the extra dimensions were to change over time, even by a minuscule amount, it would cause the fundamental constants in our 3D world to vary. The potential energy of the fields that stabilize these extra dimensions is called the radion field, and it could be the source of dark energy. If this radion field is slowly evolving, it would not only drive cosmic acceleration, but also cause the constants to change. Astronomers have been searching for evidence of such variations for years. By looking at the light from extremely distant quasars, they can study the absorption lines from gas clouds that the light passed through billions of years ago. The spacing of these spectral lines depends on the value of the fine structure constant at that time and place. Some controversial studies have claimed to find tiny variations, suggesting that electromagnetism might have been slightly weaker in the distant past. While these results are still debated and require more confirmation, they represent a tantalizing hint. If confirmed, the discovery that the fundamental constants are not constant would be a revolution on par with the discovery of quantum mechanics. It would be powerful evidence for extra dimensions and would strongly suggest that dark energy is not a simple cosmological constant, but a dynamic field linked to the very geometry of a reality larger than our own. The force pushing galaxies apart would be the same force that is subtly, imperceptibly, rewriting the laws of physics over cosmic eons. Let's confront the philosophical implications head-on. If our universe is just one brane in a vast multiverse, it represents the ultimate Copernican demotion. First, Copernicus showed that the Earth is not the center of the solar system. Then Shapley and Hubble showed that our Sun is not the center of the galaxy, and our galaxy is just one of many. The Big Bang Theory showed that our moment in time is not eternal. Now Brane cosmology suggests that our entire universe, our entire reality of three spatial dimensions, is not the center of existence. It may be nothing more than a single, unremarkable membrane in an infinite dimensional bulk, one of countless other worlds. This can feel unsettling. It can make our existence seem insignificant, but it can also be a source of profound wonder. It suggests that the reality we perceive is just a sliver of the whole, that the universe is infinitely more strange, complex and magnificent than we have ever dared to imagine. It recasts the question, are we alone? From a query about life on other planets to a query about entire other universes with potentially different physical laws. It also reframes the mystery of dark energy. It is no longer just an anomaly in our cosmological models. It is a clue. It is a window, a gravitational shadow cast upon our cave wall, hinting at a vaster world outside. The accelerating expansion of our universe could be the first tangible piece of evidence we have ever found for the existence of other dimensions and other universes. It might be the cosmos knocking on our door, inviting us to look beyond the confines of our own brain. This perspective demands a certain humility from us as scientists and explorers. We must be open to the possibility that the ultimate laws of nature are not to be found within our universe, but are written in the language of the bulk. Our search for a final theory may require us to think not just outside the box, but outside of our dimension. The phantom force is not just a problem to be solved, it is a signpost pointing the way towards a new and much larger map of reality. So, where do we stand today in this grand quest? Is dark energy a property of space itself, a dynamic field, a modification of gravity, or a phantom from another dimension? The honest answer is, we don't know. We are at a genuine frontier of human knowledge. Each of these possibilities has its own theoretical elegance and its own profound challenges. The cosmological constant, or vacuum energy, remains the simplest explanation that fits the current data. It is the leading contender in our standard model of cosmology, known as lambda CDM, lambda for the cosmological constant, and cold dark matter. However, the incredible fine-tuning problem associated with its theoretical value makes many physicists deeply uncomfortable. It feels like we are missing a huge piece of the puzzle. Models with dynamic dark energy like quintessence are appealing because they offer a way out of the fine-tuning problem, but they introduce new parameters and complexities that need to be explained. They are, in a sense, a more complicated solution. Modified gravity theories and Brane world scenarios are perhaps the most radical, but also the most ambitious. They don't just explain dark energy, they attempt to solve other fundamental problems in physics, like the hierarchy problem, and they embed our universe within a much grander structure. They offer the tantalizing prospect of unifying cosmology with the deepest questions of quantum gravity and string theory. The path forward is through observation. A new generation of cosmological surveys and experiments is coming online. The Vera C. Rubin Observatory will create the deepest, widest map of the night sky ever made. The Euclid Space Telescope will measure the shapes and redshifts of billions of galaxies with exquisite precision. The Nancy Grace Roman Space Telescope will hunt for distant supernovae and map the cosmic web. Together, these instruments will chart the history of cosmic expansion and structure growth with unprecedented accuracy. They will measure the dark energy equation of state parameter to within a percent. If they find that tau is exactly -1, it will strengthen the case for the cosmological constant. But if they find any deviation, however small, or if they uncover a discrepancy between the expansion history and structure growth, it will ignite a revolution in physics, and the ghost from another dimension will suddenly become a very real suspect. Let's explore the Kaluza-Klein tower idea, a fascinating consequence of theories with compactified extra dimensions. If an extra dimension is curled up into a small circle, a particle that is moving in that dimension would, from our 3D perspective, appear to be a new, more massive particle, Think of a particle on a carousel. It's moving, so it has kinetic energy. If the carousel is so small we can't see it, we would just perceive a stationary particle that is heavier than it should be, its extra mass coming from its hidden kinetic energy thanks to E equals mc squared. The faster it moves around the hidden dimension, the more massive it appears to us. Quantum mechanics dictates that this motion can't be just any value. It must be quantized, coming in discrete steps. This means that for any single particle in the standard model, like an electron, there should exist an entire tower of much heavier partner particles, called Kaluza-Klein, KK, modes. The first KK mode is the electron moving with 1 unit of momentum in the extra dimension, the second with 2 units, and so on, each one appearing as a new, progressively heavier version of the electron. If we could produce these KK particles at an accelerator like the LHC, it would be direct proof of extra dimensions. How does this relate to dark energy? In some models, the fields responsible for dark energy, like the radion field that stabilizes the size of the extra dimension, could couple to these KK modes. The interactions within this tower of hidden particles could influence the potential energy of the dark energy field, helping to select the small value we observe today. Furthermore, the existence of a KK tower of gravitons could lead to specific modifications of gravity at short distances. While gravity follows the inverse square law at the distances we've tested, if we could probe gravity at distances smaller than the size of the extra dimension, we would see it become much stronger, following a different power law as it spreads into the extra dimensions. Highly sensitive tabletop experiments are trying to measure the force of gravity at sub-millimeter scales, searching for these deviations. A positive result would be monumental, confirming the existence of large extra dimensions and providing a new laboratory for testing the physics that might be responsible for dark energy. One of the most profound questions in physics is whether our universe is stable. The idea of a false vacuum, which we touched on earlier, becomes even more poignant in the context of a multiverse of branes. In string theory, there isn't just one way to curl up the extra dimensions. There is a stupendously large number of possibilities, perhaps 10 to the power of 500 or more. Each of these different Calabi-Yau geometries corresponds to a different vacuum state, a different set of physical laws, and a different value for the cosmological constant. This collection of all possible universes is often called the string theory landscape. It's a vast, multi-dimensional terrain of hills and valleys where each valley represents a possible universe. Some valleys are very deep, representing stable, long-lived universes. Others are shallow, representing unstable ones. Our universe could be sitting in one of these valleys, a metastable state. It's stable for now, but it's not the lowest possible energy state in the entire landscape. There could be another deeper valley nearby. According to quantum mechanics, it's possible for our universe to tunnel through the hill, separating the valleys, and drop into this more stable state. And this is the vacuum decay event we discussed. What Brane cosmology adds to this picture is a potential trigger. The landscape isn't static. The presence of other branes, their movements, and their collisions could shake up the landscape. An interaction with another brane could provide the energy needed to kick our universe out of its comfortable valley and send it tumbling into a new one. In this view, dark energy is related to the height of our valley in the landscape. The fact that it's small and positive is what makes our universe accelerate gently. But this is a temporary state of affairs. The phantom force might not just be an external influence. It could be a symptom of our universe's own inherent instability within a much larger cosmic ecosystem. This makes the precise measurement of dark energy's properties even more critical. If we find that dark energy is perfectly constant, it might suggest our vacuum state is very stable. But if we find it is evolving, it could be a sign that our universe is slowly rolling down a hill in the landscape, heading towards an inevitable transformation. The holographic principle is another deep concept from theoretical physics that might shed light on the mystery of dark energy. First proposed by Gerard 't Hooft and later refined by Leonard Susskind, it suggests that the information content of any volume of space can be fully described by a theory that lives on the boundary of that volume. It's like a hologram, a 3D image encoded on a 2D surface. The principle arose from the study of black hole thermodynamics, which showed that the maximum entropy, a measure of information, of a black hole is proportional to its surface area, not its volume. This suggests that the information is somehow stored on the event horizon. The holographic principle generalizes this idea to the entire universe. It posits that our 3D universe could be a holographic projection of a 2D reality that exists on some distant cosmic boundary. How does this connect to dark energy and extra dimensions? In certain Brane world models, our universe, the Brane, can be seen as the holographic boundary of the higher dimensional bulk. The physics happening in the 5D bulk can be completely described by a quantum field theory living on our 4D, 3 space plus 1 time Brane, and vice versa. This correspondence, known as the ADS/CFT correspondence, provides a powerful mathematical tool. It allows physicists to translate very difficult problems about gravity in the bulk into more tractable problems about quantum fields on the Brane. In this holographic context, dark energy on our Brane could be a manifestation of a specific geometric property of the bulk spacetime. For example, the acceleration could be related to the warping or curvature of the extra dimensions. The cosmological constant problem might be resolved because the number of degrees of freedom in a holographic theory is much smaller than in a local quantum field theory, potentially taming the wild calculations of vacuum energy. It suggests that the phantom force we experience is not a force in the traditional sense, but a macroscopic consequence of the universe's fundamental informational structure. We are not being pushed by a substance, but by the emergent properties of a cosmic hologram, whose true workings are written in a lower dimensional language on the boundary of reality. Let's consider the timeline of our universe and the role dark energy plays in it. For the first approximately 9 billion years after the Big Bang, the universe was dominated by matter and radiation. Gravity was king. It was during this period that all the rich structure we see today formed. Gravity pulled gas and dark matter together to form stars, galaxies, and the great filaments of the cosmic web. The expansion was slowing down, giving gravity time to do its work. If dark energy had been much stronger from the beginning, none of this would have happened. The initial expansion would have been so rapid that gravity would never have had a chance to pull matter together. The universe would be a near-uniform, cold, empty void. The fact that there was this long, gravity-dominated era is crucial for our existence. But around 5 billion years ago, as the universe expanded and the density of matter dropped, dark energy took over. We have now entered the dark, energy-dominated era. This transition marks a fundamental change in the character of our cosmos. The era of structure formation is slowly coming to an end. The accelerating expansion is starting to isolate galaxy clusters from one another. In the far future, any civilization looking out into the night sky will see a much lonelier universe. All the galaxies outside our own local group will have been pushed beyond our cosmic horizon, their light unable to reach us, forever lost. The night sky will become dark and empty, with only the stars of our own Milkomeda galaxy, the future merger of the Milky Way, and Andromeda, remaining visible. This raises a curious coincidence problem. Why are we living at this special cosmic moment when the density of matter and the density of dark energy are of the same order of magnitude. In the past, dark energy was negligible. In the future, matter will be negligible. We seem to be alive at the cusp of these two eras. Brane world models and the anthropic principle offer a potential answer. Perhaps life can only arise during this transitional period. In a matter-dominated universe, conditions might not be stable enough for long enough. In a dark, energy-dominated future, the lack of new infalling material might stifle star formation. Maybe the conditions for intelligent observers are intrinsically linked to this specific cosmic epoch, explaining the coincidence not as luck, but as a selection effect. A key feature that distinguishes modified gravity and brane world theories from standard dark energy models is the possibility of screening mechanisms. If gravity is modified on large cosmological scales to explain acceleration, we need a way to ensure that it still behaves like normal Einsteinian gravity on small scales, like in our solar system, where general relativity has been tested with incredible precision. A screening mechanism is a clever physical process that hides the modifications to gravity in dense environments. For example, the chameleon mechanism proposes that the field responsible for modifying gravity, the scalar field, has a mass that depends on the local density of matter. In the near-empty vacuum of intergalactic space, the field is very light and can act over long distances, causing cosmic acceleration. But inside a dense environment like a galaxy or our solar system, the field becomes very massive and its range becomes extremely short. It effectively gets screened or hidden, and gravity reverts back to what Einstein predicted. Another example is the Weinstein mechanism, which is crucial for theories like the DGP model. It suggests that in the vicinity of a massive object, non-linear interactions of the gravitational field become very strong, effectively shutting off the modifications and restoring general relativity. These mechanisms are not just mathematical tricks, they are an essential part of making these theories viable and testable. They predict that there might be specific environments in the no-man's land between the dense inner parts of galaxies and the vast cosmic voids where these screening mechanisms are not perfectly efficient. In these intermediate density regions, we might be able to observe subtle deviations from general relativity. Astronomers are actively looking for such effects by studying the dynamics of dwarf galaxies orbiting larger ones, or the behavior of gas and stars at the outskirts of galaxy clusters. Finding evidence of a breakdown in gravitational law in these specific regions would be a monumental discovery, strongly favoring a modified gravity explanation for dark energy and hinting that the phantom force is a feature of gravity's complex dimension-hopping nature. The idea of dark energy leaking from another dimension fundamentally alters our perception of energy conservation. In our familiar 3D world, the first law of thermodynamics states that energy cannot be created or destroyed, only transformed. But in an expanding universe, this concept becomes more complicated. Even in standard cosmology, the energy of light is not conserved. As the universe expands, photons are redshifted, losing energy. Where does this energy go? It goes into the gravitational field, into the expansion of space itself. In a brane world scenario, the situation is even more extreme. If our brain can exchange energy with the bulk, then energy is not conserved on our brain alone. Energy can literally appear from or disappear into another dimension. The phantom force of dark energy could be a direct manifestation of this process, a continuous flow of energy from the bulk onto our brain, causing it to accelerate. This would mean that the total energy of our 3D universe is not constant. It is increasing over time. This might sound like it violates the laws of physics, but it doesn't. It just means that our brain is not a closed system. The conservation of energy would still hold for the entire higher dimensional multiverse system, Brane plus bulk. We are simply an open subsystem experiencing the effects of a larger reality. This could also have implications for the very beginning of the universe. The question of where all the matter and energy in the Big Bang came from is a classic puzzle. In some Brane world scenarios, our universe could have been born from a quantum fluctuation in the bulk, a process where a vast amount of energy was borrowed from the bulk to create our brain. The phantom force we see today could be a faint echo of this violent energy-leaking birth, a constant trickle from the same dimensional wellspring that first gave rise to our cosmos. The acceleration of the universe, in this view, is not a new phenomenon, but a deep and abiding connection to our higher dimensional origin, a reminder that our universe is not an island, but part of a much larger continent of reality. Let's bring our journey full circle, back to the phantom force itself. If dark energy is from another dimension, what does that imply about its nature? It could mean that dark energy is not an energy in the way we usually think of it. It's not a field or a particle that you could ever hope to bottle in a lab. It is a purely gravitational effect, a geometric distortion. It's the universe's response to the presence of the bulk. Imagine a taut, rubber sheet representing our space-time. In the standard view, dark energy is like a uniform upward pressure from below pushing the sheet up. In the extra-dimensional view, the acceleration is caused by the way the rubber sheet is embedded in a higher dimensional structure. Perhaps the scaffolding holding the sheet is itself expanding, or perhaps the sheet is sliding downhill in a warped higher dimensional geometry. The force is an illusion caused by our limited 3D perspective. This also offers a new way to think about the W parameter, the equation of state. We've been trying to measure W to figure out what kind of substance dark energy is, but if it's a geometric effect, W might not be a fundamental property of a substance, but an effective parameter that describes how the modified geometry mimics a fluid. In some Brane world models, it's possible to get an effective W that is less than -1, the phantom energy case, without any of the theoretical problems that plague actual phantom energy fields. The universe behaves as if it's filled with phantom energy, leading to a big rip scenario, but it's caused by the underlying geometry, not by a substance that violates energy conditions. This is a crucial distinction. It means that observing a phantom-like behavior would not necessarily mean our universe is doomed to a violent end. It might just be a sign that we are living in a specific type of Brane world. The ultimate fate would depend on the full, unknown physics of the bulk. The phantom might be terrifying in its implications, but it might also be our most direct clue, our clearest signpost pointing us away from the familiar world of particles and fields and towards the strange, beautiful, and hidden architecture of extra dimensions. The ghost in the cosmos might just be a reflection of the house it haunts. Ultimately, the quest to understand dark energy is about more than just cosmology. It's about our place in the universe and the future of physics. For nearly a century, physics has been guided by the principle of reductionism, the idea that you can understand complex systems by breaking them down into their simplest, most fundamental components. We built the standard model of particle physics this way, discovering a zoo of particles and then finding a beautiful, simple mathematical structure that described them all. Dark energy challenges this approach. It is not something we can isolate and study in a lab. Its effects are only visible on the largest possible scales. It may not be a thing at all, but an emergent property of space-time, geometry, and information. The solution may not come from building a bigger particle accelerator, but from a new conceptual revolution, a paradigm shift as profound as the ones brought about by Newton, Einstein, or quantum mechanics. The Brane world hypothesis is a candidate for such a revolution. It suggests that the next layer of reality is not to be found by looking at smaller and smaller scales, but by looking for larger and larger dimensions. It unites the very large, cosmology, with the very small, string theory, in a way that no other framework has managed to do. It tells us that to understand why galaxies are accelerating away from us, we may first need to understand the quantum vibrations of a 10-dimensional string. Of course, it may be entirely wrong. The explanation for dark energy could be something far simpler or something far stranger than we have even begun to imagine. But the journey itself is what matters. The mystery of the phantom force has pushed us to ask the deepest questions we can ask. What is space? What is time? Is our universe all there is? It has forced us to confront the limits of our knowledge and to dream of realities beyond our own. The darkness that covers 70% of our universe is not just an empty void, it is a canvas, and on it we are painting our most audacious and imaginative theories of everything. The ghost in the cosmos is a reflection of our own quest for understanding, a phantom that will haunt us, inspire us, and drive us forward into the unknown. We have journeyed from the observable fact of an accelerating cosmos to the very edge of theoretical physics. We've seen how a simple observation of distant dying stars forced us to confront the existence of a phantom force, a dark energy that dominates our reality. We've weighed the leading suspect, Einstein's cosmological constant, and found it burdened by a crisis of cosmic proportions. And we have dared to peek behind the curtain of our own reality, to ask if this phantom is a ghost from another world, a force leaking through from a hidden dimension. The idea that our universe is a mere brane in a higher dimensional bulk is one of the most profound and challenging concepts ever conceived, yet it offers elegant solutions to some of physics' deepest puzzles and provides a cosmic stage vast enough to contain our wildest questions. We do not yet know the truth, but the search is underway. In the patterns of ancient light, in the collisions of subatomic particles, and in the delicate dance of galaxies across billions of light-years, we are hunting for clues. Thank you for joining us on this exploration of the ultimate unknown. The universe is speaking to us in the language of acceleration. The question is, are we clever enough to understand what it's saying? If you could ask the universe one question about dark energy, what would it be? Let us know in the comments below.